Now, one thing we didn't do in this example here is we don't have a state of matter for the calcium phosphate. I know NaCl dissolves in water, but I'm not sure if calcium phosphate dissolves or not. So your book has this chart to help you figure this out. And there's about 1 million other versions of this chart, but they're all called solubility charts. And so what this chart gives us is the information that if we find on the top is all the negatively charged particles, the anions. So we find phosphate right here. There's our phosphate. And we kind of go down that row. It looks like phosphate is almost always a solid. So insoluble, the red, means that it would be forming a solid in water. Green is soluble, so that means it would be aqueous. Okay, so let's see, where's calcium on here? Oh, here it is. It's this row. So basically, this says nearly insoluble, and it's a red box. So over here, instead of writing aqueous, since it says it's, insoluble, or at least nearly insoluble, we're going to write solid instead of aqueous. Okay, so this reaction, writing these reactions and this whole process here should be reviewed from 111. And so practicing it a little bit should bring it all back to you. So make sure you check out the end of the chapter problems. Or you can come and ask me for worksheets to practice this if you're struggling. But the only thing that's new in this chapter, the only thing new for us about writing reactions is identifying whether it's going to be aqueous or solid. And so basically you just use this chart. If it's a red box, the combination of your cation here and your anion here, if it leads to a red box like this, then you write solid. If it leads to a green box, then you write liquid. Well, not liquid, that was wrong. You write aqueous, right? So the green boxes mean AQ, and the red boxes mean solid. Now, you're not going to have this chart on the final exam, so we need to start to find patterns. For example, that phosphates are almost always solids in water. The only exception to that is ammonium. And if you look at ammonium all the way across the table, it's green. Ammonium is always soluble. It doesn't matter what you pair that with. So NH4 plus, it's another one of the groups on the back of your periodic table. Always soluble. So if I wanted to make phosphate dissolve in water, I would do that by putting it with ammonia. Anything else and it would be a solid. But ammonia will dissolve. And there's a few other groups like that. Chlorate, for example, always soluble. Chloride is almost always soluble. There's really only one exception on this table, and that's lead. It turns out that mercury and silver are also exceptions. If you put mercury and chlorine together, it will form a solid, and the same thing for silver and chlorine. But you can make general statements like chlorine is always soluble except when mixed with lead, 2+, mercury, and silver. Okay, so look for patterns like that. Nitrates, here's another one. Nitrates, always soluble. There's no exceptions to that. Okay, so you can find patterns in here. Acetates, almost always soluble. Bromine, almost always soluble, like that, okay? The same rules that apply to chlorine apply to bromine. So it's just that when you mix it with lead, mercury, or silver, it forms a solid. But every other thing you mix it with, it's going to be aqueous. All right. So I want you to pick 2 of these problems. They're already balanced, okay? I've already written the states of matter for you. But what I want you to do is pick any 2 and write the net ionic equation for it. All right, and remember that aqueous substances ionize, meaning they separate into ions, and solid, liquid, and gas particles don't. They stay the way that they are. So we're not going to change anything about it in the ionic equation. Okay, so the next part of this chapter deals with a different type of reaction we've studied before, which we called single replacement reactions. They can also be called single displacement, and they can also be called redox reactions. So they have a lot of names, but they're all the same thing. In order to understand these kinds of reactions a little bit more, we want to remember some facts that we know. Atoms always want to be stable, and so the question here is, what is the most stable group on the periodic table? And the answer to that is the noble gases. We know they don't like to react with anything because they're so stable. They have 8 valence electrons, so everybody wants to get to 8. Now, if I'm in group 17, it's a lot easier to find 1 electron from somewhere else to become like the noble gases. So in other words, like if I have fluorine, it's going to gain an electron from somewhere to become isoelectric, meaning the same electron structure as neon. That's a lot easier than giving up 7 electrons to become like helium, right? It's going backwards. Okay, so that concept that we learned in 111 applies directly to this. And so the single replacement reaction shown here is just iron, it's a nail, being added to hydrochloric acid. And so the reason I know it's a single replacement reaction is because it's starting with an element. Iron in the solid form is an element. And it's mixing it with a compound. And when we do that, what happens is the element will react. And so we know that metals like to become positively charged, like Fe2+ here. So that means that the H is going to get kicked out because the H is positively charged in HCl. And so what it does is the element replaces the cation, and so we get iron and chlorine together here. And to replace it, we have to produce the element hydrogen. Now, this means we need to remember the diatomic elements. And if you had me for 111, I gave you a little saying to remember it by. And that is have, H, no fear of ice, cold is chlorine, beer. So these 7 elements are the diatomic elements, okay? So if I have hydrogen ion and I want to kick it out to make it into its element form, it has to be as H2, always. You can't make just H, it doesn't exist. H plus does, but that would be a double displacement, not a single replacement. So effectively, a single replacement reaction, what you're doing is you're taking an element with no charge and you're turning it into an element with a charge, in this case 2+. And then in order to like balance the scales, sort of, we have to take the charged hydrogen, this is H3O+, and turn it into the not charged version of hydrogen. So they're like trading places. Electrons are literally moving from one of them to the other one. Okay, so we can write the metal reactions as a series of what we call oxidations. Oxidation means that the element loses electrons. So for example, lithium is capable of losing an electron. So the element lithium, so this is the element, that would be solid, produces the ion, Li+, and an electron. Okay, so basically we're saying that it gives up an electron, which we already know that lithium does that because it's in group 1. Barium will give up 2 electrons because it's in group 2, and so does calcium, on and on like that. All right, and so different metals are willing to give up their electrons to various degrees. The quickest one, the easiest one to give up an electron is lithium. The hardest metal, the one that doesn't like to give up electrons, is gold. That's why we use gold in money, because if every piece of gold you had gave up its electrons anytime it touched another metal, then you would eventually have a bunch of aqueous gold and no actual money. But since gold is on the bottom of our activity series, that tells us that it isn't a very active metal. And so this series is pretty cool because it lists everything by how easy it is to take electrons from it. And so interestingly, if I take an element, say like lithium, and I react it with any of the ions below it, so let's say, I don't know, aluminum ion. If I combine lithium metal and aluminum ion, it will create a reaction that we call redox. That's a single displacement reaction. So if I have an element that is above the ion, then the reaction will go. However, if I have a situation where I am mixing the ion of lithium with the element aluminum, nothing happens. Okay, so that's one way we can use this chart. So looking at this reaction here, we can see that this is the first reaction in red. We're mixing the ion of iron 2 plus, because it's in a compound as FeCl2, with magnesium the metal. So here's magnesium the metal, here's iron 2 plus. The element is above the ion, so this reaction will go. Okay, the next pair is between aluminum chloride and copper. So, let's make that a different color actually. So aluminum chloride and copper. Aluminum chloride is the ion, so that's Al3 plus, and copper is the metal, which is in blue right here. Okay, so the ion is above the element, so no reaction occurs. Nothing happens. Okay, so just by having this tool, this one chart, we can tell whether any combination of single displacement reactions is going to occur or not. For example, if I mixed HCl, if I mixed HCl, which is really just H plus ion, with, let me see, if I mixed HCl with aluminum foil, those two would definitely react because the metal is above the ion. But if I mixed HCl with, say, platinum down here, it won't react. Nothing happens. Okay. So the farther down in the series we go, the more stable the metal is, or the higher up we go, the more active it is. However you want to think of that. Okay, so in order to remember what oxidation and reduction mean, we have a little saying. Leo says ger. So this means the loss of electrons is oxidation. That's Leo. And so the other part of this is the gain of electrons is reduction. Okay, so oxidation is what happens when things lose electrons. Reduction is what happens when they gain electrons. So like this process of lithium going to lithium plus and 1 electron is producing an electron. So it's losing an electron. You're giving it away. So that means it's an oxidation. So this activity series is actually also a listing of oxidation strength. Lithium is the strongest to be oxidized, and gold is the weakest. Okay. So you have to have both pieces. You couldn't just have the lithium metal by itself producing electrons. That electron can't exist by itself. So it's got to have somewhere to go. So you got to have sort of pairs. One of them is oxidized, the other one is reduced, and this happens simultaneously. Okay, so they always go together. Now, this is particularly interesting because redox reactions are what make up all batteries. Any battery you've ever used is a redox reaction. There's basically 2 types of batteries. There's wet batteries and there's dry batteries. So this is a diagram showing a wet battery. And basically, what you have is a solution where you've put some zinc sulfate in water and a zinc strip. And at this portion of this electrochemical cell, the reaction is producing 2 electrons.